In this video, I wanted to talk a little bit about what we refer to as solving limits algebraically. And essentially what it boils down to are a bunch of rules for solving limits that allow us to break them down into parts and solve them piece by piece by piece. And they all rely on some common sense about limits in general. In your guys' notes, I left some room for you to try to write your own explanation of how you can think about it, but I'll go through it a little bit in this video. But I wanted to start with a couple examples of particular functions and their limits, specifically limits of just a variable x by itself, as well as limits of a constant. So in this example in your notes, I've given three example functions where lowercase f of x is defined to just be x, called the identity function. And then we have a lowercase g of x function defined to be 3, which we sometimes call a constant function or horizontal line. And then also we're looking at capital F, which is the sum of lowercase f and g put together. And just what I wanted to demonstrate is how does a limit work with x by itself, as well as the limit of a constant, as well as what happens if we then take limits and add them together. So let's start with lowercase f of x, which is just x. And below the graph, in previous videos we've covered solving limits numerically, algebraically, graphically and numerically. And I wanted to kind of elaborate and say, well, what's a more general way of doing it so that we don't always have to look at a graph or plug in numbers, because that can take some time and thinking. But let's say we're concerned about what's the limit as x approaches 2 of f of x, or another way we could write this. Sorry, let me make sure my tablet is working. The limit as x approaches 2 of just x by itself. And this is essentially one of the points of this video is, what is the limit of just x? Well, if we look at it, if we're using the graphical method, well, we're focusing on what happens as x approaches 2 on the function itself. And if we're looking at the function, it is well defined at 2. Of course, if we plug into f of x, we get 2. And the limit is not about what is f of 2, but it's about what happens as we get close. And we can see from the left and from the right, both directions, the limit of the function is approaching 2 on both sides. It's getting closer and closer and closer to the value of 2. And so since both limits are in agreement, we say that the limit as x approaches 2 of x is just 2. And sometimes we might call this the substitution rule for a limit, but at the end of the day, with x, we're allowed to plug 2 in from the limit because the function is well defined. And to me, there's some common sense in this, is that if we're trying to figure out, well, what's happening as x approaches 2, if we just have x, well, we know what's happening as x approaches 2. It's 2, right? Because the target of the limit is the same as the variable itself. And of course, as we approach 2, x is just the same as the direction of the limit. So, and this is a general thing you can apply. Like, say we're looking at, well, what's the limit as x approaches -5 of x as well. Basically, we don't need to think about it. You can just plug in -5 and we're good to go. And now, quick word of caution, this does not work for any algebraic expression or function. This only works for if you have x completely by itself. And taking this idea, we can elaborate on into other circumstances and think about, well, are we allowed to plug in the value of x into the limit or not? That is not always the same. But, say we were to looking at 5 as well, right? Of course, at 5, as we approach 5 from the left and the right, the value of f of x, or x, is approaching 5. Now, if we take a similar line of thinking towards the constant function g of x being 3, and again, say we were to plug this in, because our function g is always going to be 3 in this example, and the question is, well, what's happening as x approaches 2 of 3? And so this is a fairly different situation, because the question is, well, what do we do? If there is no x within our limit, how do we evaluate? But if we, again, look at the graph, as we approach 2, that's the target of our limit if we're using that wall method. From the left and from the right, the value of the function is constant. Well, this function is always 3 regardless of what x is. So as we're getting closer and closer to 2, well, the value is 3 regardless. And this is my point about this example, is that the limit as x approaches 2 of a constant, well, it actually doesn't matter where it's approaching. the limit of a constant is the value of the constant. And similarly, say we were looking at -5, again, both from the left and from the right, the value of the function is constant at 3. So as we'd say, the limit as x approaches -5 of 3 is still 3. And these patterns are what I wanted you to notice, is that if we have x, the limit of x is just the target of the limit plugged directly in, or you can think about it as a substitution. If you plug in 2 in for x, you get 2. It's just like taking x and plugging in. And similarly, if we have a constant and we want to know what's happening as the limit approaches 2 or -5 or wherever, well, there is no x. So as x approaches 2, the 3 does not care about x because it's just a constant value. So it's not going to change. It's going to maintain its value of 3 regardless of it. And these ideas can be sort of summarized by the limit of x is just equal to a, the target of the limit, and the limit of a constant is equal to c, the value of the constant, regardless. And lastly, this video is getting a little longer than I intended. The question is, what happens if we combine the two functions together? What about the limit of x plus 3? How would we determine that? So say we are looking at 2 as a target right here. We can see, well, the limit of x plus 3, in both directions, it appears to be heading towards, as x approaches 2 from the left, the value of the function gets close to 5, and as x approaches 2 from the right, the value of the function also approaches 5. So both are in agreement. We'd say that this limit is 5. And one thing I wanted you to notice is what we actually end up with is the limit of f of x. Again, another way I could have written capital F of x. Sorry, I should have specified that I'm using capital F of x here. Is, well, capital F of x was equal to lowercase f of x plus lowercase g of x. And each of those limits we'd already figured out. You know, the limit of x is 2, the limit of 3 is 3, because x cares about where we're headed to, 3 does not. And those ideas could be said in the same way. Well, this is going to be equal to the limit as x approaches 2 of x plus 3, because those were the values of each of those functions, aka f combined. But essentially, if we know the limits of each of those individually, this will be equal to the limit as x approaches 2 of x plus the limit as x approaches 2 of 3. And the limit as x approaches 2 of x is just 2. 2 plus 3 is 5. And that's what we get. Sorry, my face is in the way there. That's what we get after all is said and done. Now, sorry, I wrote that in a lot of different ways. And if I got a little bit confusing about the point I'm trying to make here, is that, well, I'm trying to emphasize another rule for limits, and those are what we sometimes call limit laws. And limit laws are how we solve limits algebraically. I'll post one more video about the laws and how we use them. But at the end of the day, there are some major takeaways. I don't want you focusing too much on the rules and focusing more on the sensibility, in that, well, in this case, the limit of x is just equal to the target of the limit. The limit of a constant is always equal to the target, aka it does not change anything. And if we try to add individual components of a function together, the limit is maintained as the sum of the individual limits. Which one way I might refer to this is limits can break across addition. If we're adding two parts of a function, I could take the limit of this and this separately. And my point was, we already know how to solve the limit of x, and we know how to solve the limit of 3. Those always solve the same way. And so similarly, say we wanted to know the limit as x approaches 5 of f of x. Sorry, I kind of used a lot of space here. Well, capital F of x is just x plus 3. Again, once again, we have our function, and if we were trying to solve this algebraically, again, we could use the graph, but my whole point here is, well, I know the limit of x is just going to be -5, and 3 will not change. So it's TLDR, I can sub in -5 plus 3 into my limit. I can plug that in. What I end up with is the limit value of -2. And I can, that's what we would say as solving the limit using algebra, as opposed to using a number or graph. And we can always check our limits with a graph or with numbers, because again, if I'm double checking the graph, notice this is consistent. As x approaches -5 from either the left or the right, it's getting closer to the value of -2. In other words, I can just evaluate it There are some cases where you cannot just evaluate the function at -5, however, which we will be focusing on more when we talk about continuity.